Next, we will talk about composites and composite structures. Composites can be defined as a combination of two or more materials working together. Each contributes its own structural properties and each retains its unique identity. Composites synergistically combine these two materials into something much better. Wood is a natural composite and consists of fibers reinforced with resin. Wood has very similar protective properties to composites. It does not corrode, it has very high fatigue life, and it has a relatively low radar signature. Non-metallic materials, also known as composite materials, offer many advantages over other materials. Within aerospace markets, where exceptional performance is required but weight is critical, composites continue to grow in importance. Some of the many advantages of composites are stronger and stiffer than metals on a density basis. For the same strength, they are lighter than steel by 80% and aluminum by 60%. Highly corrosion resistant. Most composites are essentially inert in the most corrosive environments. Outstanding durability. Well-designed composites have exhibited apparent infinite life characteristics, even in extremely harsh environments. Low investment in fabrication equipment. The inherent characteristics of composites typically allows production to be established for a fraction of the cost that would be required in metallic fabrication. From virtual to real is the track that aircraft follow. Here the Boeing 787 Dreamliner takes shape. Its fuselage, made of composites, consists of 4 cylindrical sections. Composites, because of their lightweight and strength, are gaining favor as a material for aircraft. The Boeing Company's 787 Dreamliner, officially unveiled on July 8, 2007, has become the poster child for composites in aircraft design because the design uses materials extensively. According to Boeing, composite materials constitute about 50% of the aircraft by weight. Several composite materials used in the aerospace industry are carbon graphite, fiberglass, Kevlar, and thermoset plastic. Carbon graphite. Carbon graphite fiber composites are noted for their stiffness and high compressive strength. One of the problems with carbon graphite as a structural material is the fact that aluminum alloys in contact with it will corrode. For this reason, fasteners used with carbon graphite must be made of corrosion-resistant materials such as titanium or corrosion-resistant steel. Fiberglass. There are 2 types of glass fibers used in the aircraft composite structure, E-glass and S-glass. E, or electrical glass, has a high resistivity and is designed primarily for electrical insulation. Its low cost makes it the more widely used type of glass where high strength is not required. S, or structural glass, has a high tensile strength and is used for critical structural applications. Kevlar. Kevlar is an aramid fiber that is noted for its flexibility and high tensile strength. It does not conduct electricity and does not cause aluminum to corrode when it is held in contact with it. Thermoset plastic. A class of plastics that, when cured by normal thermal and/or chemical means, become substantially infusible and insoluble. Once cured, a thermoset cannot be returned to the uncured state. Some of the more common thermosets include epoxies, polyurethanes, phenolic amino resins, and polyamides. This section is designed to familiarize you with the materials and processes associated with the aerospace industry. Next, we will talk about some of the composite manufacturing processes used in the industry, such as wet layup, vacuum bagging, prepreg layup, filament winding, press molding, resin transfer molding, and resin infusions. Wet layup. The manual wet layup is the oldest and simplest composite technique. It usually requires use of a tool or mold and requires a release agent. The surface can be wet or sprayed with resin or a gel coat. The gel coat is allowed to partially cure before the addition of fabric. The fabric can be applied dry, saturated with resin, or sprayed with chop gun. Excess resin is then removed by hand working. Vacuum bagging is a technique employed to create mechanical pressure on the laminate during its cure cycle. Pressurizing a composite lamination serves several functions. First, it removes trapped air between layers. Second, it compacts the fiber layers for efficient force transmission among fiber bundles and prevents shifting the fiber orientation during cure. Third, it reduces humidity. Finally, the most important, the vacuum bagging techniques optimize the fiber to resin ratio in the composite part. This is an example of a vacuum bagging process. In the vacuum bagging process, you will normally use a bagging film, release film, breather material, bleeder material, and peel ply. A call plate is placed in immediate contact with the layup during curing to transmit normal pressure and provide a smooth surface on the finished part. Pre-preg material can be used in the vacuum bagging process. Pre-preg fiber is pre-impregnated with resin, hence the name. In this diagram, consolidation involves the cutting and stacking of pre-preg layers in a predetermined sequence of fiber orientations. The matrix resin is cured by exposure to a defined combination of temperature and pressure. This diagram shows how pre-preg fabric is manufactured. The fibers and matrix film are joined together, heated, and then rolled with release paper to keep it from bonding. Pre-preg must be stored at below 0 degrees Fahrenheit, and its shelf life is only up to 1 year. With filament winding, a large number of fiber rovings are pulled from a series of creels into a bath containing liquid resin, catalysts and other ingredients such as pigments and UV retardants. Fiber tension is controlled by the guides or scissor bars located between each creel and resin bath. Just before entering the resin bath, the rovings are usually gathered into a band by passing them through a textile thread board or stainless steel comb. Press molding. Press curing uses heated platens to apply both pressure and heat to the part. Presses in general operate at 20 to 1000 psi and up to 600 degrees Fahrenheit. Press curing is very economical for flat parts and high production rates. Tooling requires matched die molds for contoured parts.